Okay, so the term carbohydrate refers to a chemical compound made up of carbon atoms that are fully hydrated. So carbo for carbon and hydrate for hydration or water. And because these biological molecules are hydrates of carbon, you can find them fitting into the general formula C, so a number of carbon atoms. So N for just kind of a generic number of carbon atoms, and then a matching number of water molecules, so H2Os, usually in the exact same number as your carbon atoms. And because all of these carbons kind of have an associated water, you can think of this as being essentially a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. Now, when we have one of these carbohydrate molecules, we call it a monosaccharide. So monosaccharide. And monosaccharide essentially means one saccharide, and saccharide is just a synonym for carbohydrate. So saccharide is actually, it's derived from the Greek word for sugar. So you might hear a single carbohydrate referred to as a simple sugar. But in all these instances, we're talking about the same kind of molecule. And these molecules that we're calling carbohydrates, they do some pretty incredible and pretty hugely necessary things in our bodies and in most living things for that matter. And maybe one of the most familiar of these tasks is the fulfillment of our body's energy source. So carbohydrates fulfill our body's energy needs, and the main energy source for metabolism in our bodies is glucose. So glucose, and I bet you've heard of glucose before. If you might have heard it in the context of checking blood glucose levels for people with diabetes, but glucose is a monosaccharide made of 6 carbons, and you might also be familiar with kind of the structural rigidity of cell walls in plants, and that rigidity comes from the rigid carbon backbone of several carbohydrates linked together to form the polysaccharide. So polysaccharides, several saccharides, several carbohydrates linked together, and we call that cellulose. So cellulose is the polysaccharide, the carbohydrate that makes up the structural backbone of cell walls. And then, of course, one of the most beautiful carbohydrate roles in my mind is the use of ribose, which is a 5-carbon sugar that supports the transcribed products of our genes in RNA. And so you might have caught on that in all 3 of the carbohydrates that I just mentioned, we see the ending ose, O-S-E. And we see that in glucose, cellulose, and ribose. And that's because ose is the suffix for sugars. And there are actually 2 prefixes that help us further break down the naming of these compounds. And so the first prefix that we're going to consider is how many carbons are in the chain. So the number of carbons that are in the chain for this molecule. So for example, I'm going to draw glyceraldehyde, which is kind of generally considered to be the simplest carbohydrate. And it looks like this. And if this carbonyl group right up here was just another hydroxyl group, this would be glycerin, 3 carbons with 3 hydroxyl groups. But instead it's an aldehyde. And so this molecule is for that reason named glyceraldehyde. And the aldehyde is our functional group. And so if we're going to count how many carbons are in this molecule, we'll start with our functional group carbon, this carbonyl carbon up here, and we've got 1, 2, 3 carbons in glyceraldehyde. And so there are 3 carbons, and for that reason we would call this a triose. Tri for 3, and again ose as our suffix for sugar. And if we added a 4th carbon, we would call it a tetrose. So 4 carbons in a carbohydrate chain is a tetrose, and then we add a 5th carbon, and that would be a pentose. So pentose for 5, and if we added an additional carbon, we would have 6 carbons, and that would give us a hexose. Hex being the prefix for 6. And I mentioned before when I was talking about the energy source of our body, that glucose is actually a 6-carbon carbohydrate. And so as an example of a hexose, I'll draw glucose here. So this carbon chain, there's 6 carbons. We've got 1, 2, 3, 4, 5, 6 carbons, and this is a hexose called glucose. Now, in the case of glucose, the functional group is an aldehyde, just like our glyceraldehyde. So the functional group up here is an aldehyde. But what if we make it a ketone? You see, we can actually make it a ketone and still retain that 1 to 2 to 1 ratio, and it brings us kind of another pretty popular hexose called fructose. So this is another hexose. It still has that 1 to 2 to 1 carbon, hydrogen, oxygen ratio, but instead of having the aldehyde functional group, it has a ketone functional group right here. And so that brings up kind of the second naming prefix. We have to indicate whether we're working with an aldehyde or a ketone. So glucose would be more accurately referred to as an aldohexose. And that aldo is a reference to the fact that the functional group in this carbohydrate is an aldehyde. And fructose, then on the other hand, let me write fructose down. So fructose is a ketohexose. And again, the keto is a reference to the fact that the functional group here is a ketone. And then if we want to just kind of exhaust this kind of second prefix idea, going back up to glyceraldehyde, which we said was a triose, because the functional group is an aldehyde, this would be an aldotriose. So aldotriose. So we name based on length of the carbon chain, the number of carbons that are in the chain, and the functional group that's in our carbohydrate. And the last kind of major component of naming is the stereochemistry of the highest numbered chiral center. So again, we start with the carbonyl carbon, and if we use a Fisher projection like we did with glucose, then we go to the highest chiral center, which would be this last one, and we decide the stereochemistry of that chiral carbon. And just kind of as a shortcut with Fisher projections, if the kind of highest substituent, in this case the hydroxyl group, is on the right hand side, then it's an R stereochemistry, and if it's on the left side, it would be an L stereochemistry. So let me try to make that a little bit easier, and I'll just kind of redraw glyceraldehyde, a nice small molecule, as a Fisher projection. So we've got our aldehyde, and then we've got kind of our next 2 carbons in this chain, 3 carbons, and we have 1 chiral center in this carbohydrate, this one right in the middle here. And our OH group, you can see, is on the right hand side. So this is an R configuration. And for carbohydrates, actually a lot of the naming is associated with the guy Fisher, who invented these Fisher diagrams, but he decided, since it was an R, and the Latin for right-handed kind of is dexter, we assign a D to this configuration. And then if we kind of drew this in a mirror image, and we drew the enantiomer of it, and we had our aldehyde carbon up here, and our last 2 carbons and their hydroxyl groups. Now we see that the chiral carbon, the highest numbered chiral carbon, has its primary substituent on the left side at the bottom of this Fisher projection, and so this would be assigned an L, which is a little bit easier. And so as an example, I guess going back to the glucose, this would be a D aldohexose, because the hydroxyl group is on the right hand side of this molecule. And again, with our fructose, same thing. The last chiral carbon has the OH group on the right hand side, so this is a D ketohexose. Now, before I move on, I want to allow you to review Fisher diagrams, because I know I just kind of blazed through it, and really they're important, especially with carbohydrates, because stereochemistry becomes quite important in the biological implication of carbohydrates. So I included a great video by Jay with Khan Academy on Fisher projections, and it's actually the video I used to learn about them. So I'd encourage you to kind of pause here for a second and give that video a watch on Fisher projections and get real comfortable with absolute configuration, and then we'll move forward with the discussion of carbohydrates.